Okay, welcome to Psych 101 General Psychology. Today we're talking about the second half of the chapter on sensation and perception. So we're going to talk about perception. We already talked about sensation, which is mostly how the senses work. Today we're talking about perception, which is how basically the brain or the mind creates meaning from information gathered from the senses. So here's a definition for you guys of perception. What is perception? It says perception is the process of creating meaning from sensory information. Okay, so perception is involved, for instance, when you know a collection of sounds is a song. Okay, it's one thing for you to say, I hear something. It's another thing for you to say, that's a song, or that's this song, okay? Or for you to say that an array of lights is a rainbow. It's one thing to say, for you to say, I see something. It's another thing for you to say, it's a rainbow. Or something you eat is a cupcake, for instance. So it's one thing for you to taste something, and it's nothing for you to know what it is, okay? Perception takes place in the brain. It's the brain that understands all those things, okay? The brain creates meaning from the sensory stimulation, okay? From the energy, basically. Remember, the senses take in the physical energy and then create it to an electrical signal. The electrical signal is then sent to the brain, and the brain makes sense of it. When the brain makes sense of it, that is called perception. And perception is more interesting than sensation. Okay, so we're going to talk about this stuff, okay? And we're mostly going to talk about visual perception, okay? Because human beings are mostly visual. But I'll mention some things here and there that maybe are not visual, but it's mostly just vision, okay? So here's the thing. Before we talk about some of the interesting stuff, I want to tell you guys that perception is more complicated, okay? So perception is when the brain makes sense of it, makes sense of the sensory stimulation, okay? So perception, actually, when you make sense of things, that involves what we call both bottom-up and top-down processing. Bottom-up processing, it says, refers to the fact that perceptions are built from sensory input. Let me explain that. Bottom-up processing is basically when you get the little bits and pieces. So you see these shapes and these lines and these colors, let's say. And then your brain puts it together and you understand, oh, that's a human face, okay? That is a person. That's bottom-up processing, okay? It's also called inductive reasoning, okay? It's basically when you take pieces of information and you put it together to make a whole. It's the same thing as saying, like, okay, it's yellow, it has feathers, it has a beak, it waddles, therefore it's a duck. That's bottom-up processing. So bottom-up processing is when the brain basically takes the little bits and pieces of information coming from the senses, puts it together to give you meaning, okay? But we can also interpret things in a different way. We can also interpret those sensations, right? We can interpret how those sensations are influenced by our available knowledge, our experiences, our thoughts. So the brain also uses top-down processing. Let me explain that further. Top-down processing basically is when your brain makes use of memory, prior knowledge, basically, emotions or all kinds of things like that, to interpret what is happening, okay? So, for instance, you might see, two vertical lines and a horizontal line running through it, okay? Your brain, just from prior knowledge, would understand that that is an H, for instance, because you've seen an H before. It's in your memory. So it interprets that, it understands that instantly, because it's in memory. That's top down. So top down is basically when you use existing knowledge to interpret what you're looking at. It's also called deductive reasoning. So that would be like, it's a duck, okay? So you remember that something is a duck, right? You recognize something as a duck, and then you say, okay, well, therefore, it has feathers, it has a beak, it waddles, okay? So that's top-down processing. The brain makes use of both of those things. It takes sensory information in little bits and pieces, puts it together to give you the whole, but it also uses the whole to influence what you see. So memory also and prior knowledge affects what it is that you're looking at. And that'll become more clear as we go through the next slides. Because when it comes to top-down processing, when it comes to the brain using existing information or memory, existing knowledge to make sense of things, that is exactly what these Gestalt psychologists were arguing for. Gestalt psychologists were psychologists who took a different approach, who believed in a different approach to understanding perception. Okay, so they don't believe so much in the biological approach to perception, where you take little bits and pieces, put it together to form a whole. Gestalt psychologists believe different things. Okay, they believe something different. And here's the a quote that summarizes their philosophy. Gestalt psychologists believe that perception cannot be broken down into parts. Okay, so it's not about a bunch of little bits and pieces. Okay, they said because the whole is greater than the sum of its parts. In other words, the image, the thing that you actually see and recognize is more than just a bunch of little bits and pieces put together. And they said that visual perception is an active creation. The meaning you create from what you see is actually something that changes as it is happening. It's something that can change. And that's a quote in APA style, right? And there are the authors. There's the year in which the work was published. It actually came from a textbook. And there's the page number because it's a quote, to give you an example of APA style. If it was not a quote, it would have to be written in your own words and you wouldn't have a page number. You wouldn't have any quotation marks either. Okay, the Gestalt psychologists basically developed what they call the Gestalt laws of perceptual organization. There's going to be 6 of them. We're going to talk about them. And as we go through this will really make it clear what it is that they really believe. But they believe more in top-down processing. Okay, they believe that perception is something that you don't really break up into pieces. Okay, and that it changes as it is happening. So it's more about the whole than the little pieces. So let me explain this. Okay, so their first law of perceptual organization, the first Gestalt law, is called figure and ground. And it says that we can shift our focus from the object to the background, and vice versa, from the background to the object, right? And that will affect the meaning. That will affect what we actually see. So look at this image here. If you look at the area in black as being the object, that as being in the foreground, and the area in white as being the background, then you see something very clearly. You see someone playing a saxophone, some kind of cartoon character, okay? But if you look at it differently, where now you see the white part as the object and the black part as the background, then it becomes something different. It's a woman's face. That is the law of figure and ground, okay? That is what it says. In other words, the way we focus on things can affect the meaning that is created. Okay. And so in other words, it could be more than one thing. It's something that can change. The whole is greater than the sum of its parts. How can this be 2 different things? It's only if you believe in top down, right? The way you look at it, the way you experience it, right? The way you focus on it is going to affect the meaning. This one's easy to see, right? Here's another one for you guys, another example of figure and ground. If you look at it one way, it's one thing. If you look at it a different way, then it's something else. Your prior knowledge here should affect what you see. If you look at it the right way, you should see a dog there. It's actually a Dalmatian. And if you find the dog, then the whole image takes on meaning. And you can see there's a tree trunk in the back. You can see the shade from the canopy above that you can't see. And you can see the dog is sniffing the ground. And there's probably some leaves and dirt there, okay? If you don't focus on this correctly, then you won't be able to see the dog. You might just see some black and white splotches everywhere. How can it be more than one thing? Okay? Because of prior knowledge, because of top-down processing, you can see that this is the dog, okay? Dog that's sniffing the ground. But let's say you've never seen a dog before, okay? Or maybe you're just focusing on this differently, then you don't see that. You don't create that meaning. That is the law of figure and ground, okay? This is what Gestalt psychologists believe. that the whole, the image there, is more than just the sum of its parts. It's more than just bits and pieces of black and white. It's more than that. And it's something that actually changes. It's an active creation. You are creating this. You are seeing this because you are viewing it in a certain way. Here's another example for you guys that's very simple. This is also the law of figure and ground. If you look at it one way, if you look at the blue part as being the object, and it looks like a vase, okay? If you look at the white part as being the object and the blue part as being the background, then it looks like two faces. How can it be more than one thing? According to, the Gestalt laws, the law of figure and ground, perception is an active creation. It can change. The whole is more than the sum of its parts. Because if you just took the sum of its parts, it creates something, it would always be the same thing. But according to the Gestalt laws, according to figure and ground, right, it can be more than one thing depending on how you look at it. So in other words, what you see is affected by prior experience. Maybe if you've never seen a vase before, or a vase, whatever you want to call it, right? You may not see it. You might just see two faces. And believe it or not, your mind switches between seeing one and the other. You can see the vase or the faces, one or the other, and it can switch back and forth very quickly. So you think you see both at the same time, but you do not. Now, I will prove to you that you cannot see both at the same time. Here's another example of figure and ground, and this one is more difficult to see. And if we were doing this in person, it would be a lot more fun, okay? That image there, right? What is it that you see? Now, some of you may say that you see a young woman kind of turning away, okay? You can see that she's wearing some kind of headdress and some kind of feather on her hair there. She's kind of looking away and she's wearing some kind of fur coat or something like that. She has some kind of necklace on. If you look at it differently, you will see an old woman. For the old woman, that thing that looks like an ear, what is an ear for the young woman now becomes the eye. And what is the neck for the young woman now becomes basically the space between her nose and mouth. The necklace becomes the mouth, and she's got some kind of pointy chin. And then the whole cheek and chin of the young woman becomes the nose of the old woman. So she has a big nose, okay? So you can see a young woman, you can see an old woman. If you know how to do this, right, you can switch back and forth. You can see both of them. Some of you may not be able to see both, and that's just evidence, right, that we can shift our focus from the object to the background. The meaning can change. Perception is an active creation. That's the law of figure and ground. That's what the Gestalt psychologist said. There's lots of examples of these. You can find many more on the internet, but I just shared some with you. Now, the other laws are not as interesting, but we'll talk about them. There's the Gestalt law of proximity that says that we perceive objects that are closer together as belonging to a group. So you see here some dots, some orange dots, I guess. You can see that the ones on the left are all equally spaced. They all have the same proximity. Proximity just means closeness. So the ones on the left are all equally spaced, and they seem to make a square. The ones on the right have some added space between them, and they don't look like a square anymore. Now they look like 3 columns. So you can see how the meaning changes based on the proximity, based on the closeness. That's the law of proximity. All it says is the amount of distance between objects affects how we perceive them. It affects the meaning we create when we look at them. Here's another law that's also not as interesting, but very easy to understand. The law of similarity. The law of similarity says that we perceive objects that are similar as belonging to the same group. So here, if you look at this, what you see there, what you're going to tell me that you would say that you see X's and O's. Notice the X's and O's are all equally spaced apart, but you don't say that you see a square. You say that you see X's and O's because the X's are similar. They're seen as one object, right? And the O's are similar. They're seen as a separate object. So you say you see X's and O's because of similarity. The X's are similar. The O's are similar. The similarity affects the meaning. Here, the proximity doesn't work as well because of the lack of similarity between, the X's and the O's. So that's the law of similarity. All it really says is that if things look the same or if things look similar, we perceive them as being the same type of object or being the same. I'll give you another example. It's a bit more psychological, right? Guess what? If you're a woman, but you look like a man, people will think you're a man. That's the law of similarity. Or vice versa. If you're a man, but you look like a woman, people will think you're a woman. When people talk to you on the phone, if you have a deep voice, people will think you're a man because you sound similar to a man. And maybe you're a woman. That's the law of similarity. It says that things that are similar, we perceive as belonging to the same group, whether you're a man or a woman, you're an X or an O, right? That's the law of similarity. It's actually very simple. And then there's the law of continuity. The law of continuity says that we tend to see things as continuous. We like to see things as continuous, okay? So here we see something. And if we were doing this, in person, you would say, I see, the Big Dipper or the Little Dipper. I see this shape, right? It looks like a ladle. It's really 7 stars, but you like to see them as continuing, as forming this shape. And we imagine the shape. That's the law of continuity. And we have another one here, another Gestalt law, the law of closure. The law of closure says that when a familiar figure is interrupted, we imagine the rest of it. So if I ask you what you see here, you would say, I see a triangle. You like to see it as closed, right? You like to see it as complete. But in reality, there's 3 angles there. But you say, I see a triangle, because you imagine that the rest of it is there. Okay, that's the law of closure. Closure is basically when things, go around and you see them as closed. Okay, let's keep going. One last Gestalt law of perceptual organization, and we'll move on to something else. The law of good figure. The law of good figure simply says that we tend to perceive things as simple and symmetrical. So if I show you this over here and I ask you what it is, you would say, I see 2 squares. It's a simple and symmetrical figure, right? But in reality, those are not 2 squares. They're rectangles, okay? Because, one side's longer than the other. But that's still simple and symmetrical. You could say that there's even something more complicated there. You could say, I see a frame. A frame is more complicated. Still symmetrical, but a bit more complicated. There's a frame that goes all the way around, and then there's yellow in the middle. Maybe a frame of the sunset or something like that, or the sunrise. But a frame is more complicated. But the law of good figure simply says that we tend to see things that are simple and symmetrical. When we see people, we tend to see them as symmetrical. But if you study people closely and you take measurements, you'll see that we are not perfectly symmetrical. But the more symmetrical you are, according to research, the more attractive you are, because we like things that are symmetrical. Houses, cars, when they're symmetrical, we like them. They look good. But when you crash your car and you break up the symmetry, now it looks like a piece of junk. Well, you messed up the symmetry. Where we live, there's a bunch of Joshua trees. And we think some of them are pretty. Guess which ones we think are pretty? The ones that are more symmetrical. The law of good figure simply says that we tend to perceive things as simple and symmetrical, and we prefer these things. So we like symmetrical cars and houses and dogs and faces. We love symmetry. That's a good figure, okay? We tend to see good figures. We tend to see things as more simple and symmetrical than they actually are. That's the law of good figure. Okay, those are the Gestalt laws of perceptual organization. Now we're going to talk about depth perception. So we're going to talk about how we see distance. That's what depth perception is. Depth perception is the ability for you to see something in 3 dimensions, for you to see something as having basically distance, that it's not a flat object, okay? That's what depth perception is. And then when it comes to depth perception, there's 2 kinds of cues that you can use to basically see something at a distance or to know that something is 3-dimensional. The first set of cues are called binocular cues. And they're called binocular cues because they are cues that depend on the action of both eyes. Bi means two, ocular means that it has to do with the eyes. So binocular cues really refer to information that tells us about distance, that you need both eyes in order to see this information, in order to make use of it. And there's two things for binocular cues. There's two types. There's retinal disparity, okay? Which just means the difference in an object as seen by the left eye and the right eye. Retinal disparity, okay? If we were doing this in class, I would do this with you guys, but I'll still tell you guys about it. If you hold out your thumb in front of you like this, right, and you look at it, you close one eye, look at it with one eye, and then open the other eye and close the one that's open. So look at it with one eye and then the other. If you can wink with both eyes, you can do this easily. I have to use my hand because I can only wink with one eye. But you see that the thumb will appear to move. It's in one position and then another. Why? Because one eye, the left eye sees it in one place, the right eye sees it in a different place. You have two eyes and they see the world in slightly different ways. Your brain combines those images, by the way, so you only see one. Unless you're drunk or something like that and not doing it very well. But that's a binocular cue that tells you about distance. Because the greater the shift, the greater the difference in the position of an object as seen by the left and the right eye, usually that means that it's farther away. The less shift, the farther away it is. The more of a difference in the position of the object as seen by one eye or the other, if the difference is larger, that usually means it's closer, okay? And I can demonstrate that. Your thumb shifts a little bit when you look at it with one eye and then the other. If you look at the tip of your nose with one eye and then the other, you'll see that your nose shifts a lot more. It's closer, it shifts more. That shift is retinal disparity. One eye sees it one way, another eye sees it another way in different positions, okay? That tells your brain about distance, okay? Another cue is called convergence. Convergence is the degree to which your eyes turn in to focus on an object, okay? Again, I will tell you to look at your nose, but this time look at your nose with both eyes. Look at the tip of your nose. To look at the tip of your nose, your eyes kind of have to converge or turn in. When you look at something nearby, your eyes have to turn in or converge more. When you're looking at something that's far away, your eyes don't really have to turn in that much. That's called convergence, the degree to which your eyes turn in to look at an object, okay? That also tells us about distance. If your eyes don't converge a lot, you're looking at something that's farther away. If they converge more, you're looking at something that's closer. So those are binocular cues about depth perception, about perceiving distance. But there's also monocular cues, and monocular cues are more interesting. Now, monocular cues are called monocular cues because you only need one eye to make use of this information. Mono means one, ocular means has to do with the eyes. So this is information that you can use that tells you about distance, that tells you about depth, and you only need one eye. If you're missing one eye, you can still do this, okay? The first one is very simple. The first cue of, first monocular cue of depth or distance is called relative size. It's simply the size of an object. Closer objects usually produce larger images than those that are far away. So if you're talking about an object that's the same, right? When it's closer, it looks bigger than when it's far away. And the way your eyes are looking at it, right? You can see it with the bottom image over here. So you have two balls there, two blue balls, I guess. You can see there that this is the way it works, okay? When the ball is far away, B there, it reflects light, enters the eye, and the lens focuses that light on the retina. It stimulates a certain number of cells. When the ball is closer, it reflects light and then reflects off the, and then the lens focuses that light on the retina again. But now it stimulates a greater number of cells. So all this means, relative size, is that an object looks closer when it's, an object looks bigger when it's nearby than when it's farther away, if we're talking about the same object. When you see a plane that's high in the sky, right? You see it flying off, right? You don't say, oh, look at that little toy plane, right? No, you know that's a big object, right? and you infer that it's far away, that is a certain distance away. Not a specific distance, but you infer that it's far away. That's why it looks small. This is very important, relative size. But of course, experience also matters. I'll tell you now about a certain case study, a certain story of someone who had problems with relative size. There was an archaeologist who was studying a group of Aborigine people in Africa that were called the Bambuti Pygmy. Pygmy people are people who are very small, so they're very short, okay? And they're Bambuti Pygmy, which means they live in a bamboo forest. They live among the bamboo. And some of these Bambuti Pygmy have never been outside of that bamboo forest. And if you've ever been inside of bamboo, it grows very closely together, and everything is right in front of your face, okay? So there was this Bambuti Pygmy guy who had never been out of the bamboo forest. He was only used to looking at things up close, okay? One day, the archaeologist took one of these Bambuti Pygmy outside of the bamboo forest, took him for a ride on his truck. They went outside of the bamboo forest. And the Bambuti Pygmy guy sees buffalo grazing in the distance. And he asked the archaeologist, hey, what kind of insects are those? And the archaeologist says, those aren't insects, those are buffalo. And the Bambuti Pygmy guy basically starts laughing. He says, you're crazy, those are not buffalo, those are insects. I guess he's probably eaten some buffalo before. Maybe there's some Bambuti Pygmy that go off on a hunt and bring the meat back, bring the carcass back and all that, but he thought those were insects. He says, no, you're crazy. Those are insects. Those aren't buffalo. Those look way too small to be buffalo. So then the archaeologist drove closer and closer to the buffalo. And as he drove closer and closer, they got bigger and bigger. And then the Bambuti Pygmy guy started getting scared. He thought that the archaeologist was doing some kind of witchcraft because he had never been outside of that bamboo forest. He had never seen buffalo up close. He didn't know how big they actually were. Okay, but that's the importance of relative size. It tells us about distance. And usually, when we're talking about the same object, if it's far away, if it's small, that usually means it's far away. If it's closer, then it looks bigger. So there's some logic there, okay? That's just the size. The size of an object is basically a clue to how far away it is what I'm saying. But experience also matters. Your senses can be fooled. You might think you're seeing something when in fact it's something else, if you're not familiar with the object. And I'll give you other examples later on. Another monocular cue of depth perception is called linear perspective. Linear perspective just refers to lines that are parallel. It says as parallel lines stretch out toward the horizon, they come closer together. So here we have parallel lines. It's a road basically, and the lines are parallel. And we can see that where the lines are closer together, that is farther away. Our brain makes use of that information. It's a monocular cue of distance. It's called linear perspective. Where the lines are more spread out, that's closer. But in reality, this is just an image, right? The image, where the lines converge and where the lines are more spread apart, it's the same distance to your eyes. But because of these lines, it makes it look like it's far away. This is a photograph, okay? And that's partly how our mind makes sense of distance. And this is just a road. Okay, so a road going through the desert. Now it's not the Antelope Valley, okay? It's not that. It is actually Highway 1 that leads down to Baja, okay? When you cross the Mexican border, you go on the 1, and it goes all the way to Cabo San Lucas, right? All the way down. And me and a friend of mine, we took a trip in 2005. He took a bunch of pictures. I'm gonna share some pictures with you guys as they apply. Okay, so this is one, linear perspective. Here's another one for you guys, closeness, or not closeness, clearness or detail. How clear something looks or the detail you can see of something also tells you about distance, because we can see nearby objects in more detail than the more distant ones. You don't think about it, but that's a clue to distance. So if we look at the rock there, the big rock, we can see the cracks, right? the different shapes there, right? That rock we know is closer than, let's say, those other rocks that are far away that you can't even see. Okay, maybe you can see some of them as little dots, okay? But you can't see much detail. So that must be farther away. It's simple. Some of the plants in the front, you can see some of the individual leaves and little stems. The ones out in the distance, you can't see that. You can't see that detail, but you know, there's plants there. That's clearness, that's detail, simply what it is. You don't think about it, but when you can see a lot of detail of something, that means it's nearby. When you can't see a lot of detail, that usually means it's farther away. It's very simple, very logical. Your brain makes use of that information. Here's another monocular cue for you guys, texture gradient. Texture gradient, what that refers to is that when objects are farther away, they look more packed than objects that are nearby. So all texture gradient says is that when things are farther away, they look more packed together than things that are nearby. So if you look at this hill over here, and by the way, those rocks are a lot bigger than they look. They're really huge. You can see that as you go up the hill off in the distance, they look more packed together. They look like they're more squished together. And the ones that are closer, the ones toward the bottom, they look a little bit more spread out. But that's texture gradient. You can also see this when you're looking at a floor that has that checker pattern, that black and white. And you'll see that the checker pattern in the front or closer to you looks more spread out than the one in the back. The one in the back, they look more squished together. That's texture gradient. That's simply what it says, right? It just says that things that are far away look like they're more packed together than things that are up front. That's texture gradient. There's another one called overlapping or interposition. Now, obviously, this is not a picture that was taken in Baja, but it makes the point very clearly. Overlapping interposition just has to mean with you know, that an object blocks another. When one object interrupts or blocks another, the one that interrupts or the one that's blocking the other one, that one is closer. So here the red rectangle is blocking the blue one, and therefore the red one looks like it's closer than the blue one. But in reality, this is just a flat image. They're both the same distance away, but it gives us the illusion of distance there. And that's all that means. When you're looking out there in the real world, if somebody seems to block your view of somebody else, that someone is closer. So it's just logical, right? But our brain makes use of this information. Here's another picture for you guys. This one was taken in Baja. Okay, desert that is out there with a lot of interesting things to see. And if we were doing this in person, I would ask you, right? But I don't want you to talk because I'm recording this. I would ask you, how many monocular cues of depth perception can you spot? And you would tell me, well, I can see, you know, object size, you know, the objects, the little bushes here, the little things that are closer right there, the ones that are right up front. There's another one that's right there, closer to the bigger cactus, right? Well, the one in the front looks closer. So therefore that one in the front, I mean, the one in the front looks bigger, so therefore the one in the front is closer. You can say there's also interposition, you know, where, you know, this bush, colorful bush over here is blocking our view of that other bush that's there. So therefore that one must be closer. There's no linear perspective, there's no parallel lines, right? So there's object size, there's interposition, there's also detail. You can see more detail of the little plants up front than the ones in the back. There's also texture gradient, okay? The plants in the back, if you look past the big cactus, the ones in the back look a lot more squished together than the ones in the middle. And then the ones in the front look even more spread out. That's texture gradient. But we're not done. There are other monocular cues that we need to talk about, but I just wanted to review here to, you know, show you this example. And like I said before, object size is a clue to distance, but if you're not familiar with something, you may misjudge its size, because in that case, you're also misjudging how far away it is. And if we were doing this in person, I would ask you, how big is that cactus right there that you see, the green one that has all these, you know, different prongs or all the different extensions that go up. How big do you think that cactus is? It's not a saguaro, by the way. It's called something else. I don't remember what it's called. But I'm going to show you an image after this one that shows you basically something that can allow you to more accurately judge its size. So you can see that you're probably misjudging its distance. Here's that same cactus. And there I am right there on the left, and there's a friend of mine right there on the right. When we took this trip, you can see that cacti, no, that cactus, cactus is plural, cacti is, no, okay, that cactus is singular, cacti is plural. That cactus is a lot bigger than you think it is. When you were looking at it in the previous picture, it's actually more far away than you think it is. That thing might be 50, 60 feet tall. They grow huge, and you can see more of them in the background, okay? You might think that they're closer than they actually are because it's hard for you to believe that they can be that big, but they're farther away than they look. They're really big, and there's a whole bunch of them that grow out there. Another monocular cue of depth perception, another thing that tells you about distance or 3 dimensions is shadowing, or just shadows. Shadows give us a clue to the size of something because things that are big can cast bigger shadows. It also tells about the location because you can see the shadow where it's coming from, right? And depth. Shadows also tells about, you know, something being 3-dimensional, about depth. This doesn't really tell you about depth here, but a shadow is when you see like a building and one side is shaded and the other one is being lit by the sun, that makes it look more 3-dimensional. And when you create a drawing, you can use shading, you can use shadowing to make something look more 3-dimensional. And that is exactly what they do, by the way, when you see those animations, and they make those animations look really lifelike, or they make them look really 3-dimensional, as opposed to the old ones, the old cartoons, where the images just looked flat. They're a lot better now at creating these animations, right? Because they can do it with a computer now, and they can make it look like it's perfectly 3-dimensional, like it's basically has depth, where in the past with those drawings, they look kind of flat. All that is because of shadowing and other things as well, but shadowing is a big one that makes things look 3-dimensional. Another monocular cue of depth perception is atmospheric perspective. Atmospheric perspective simply says that objects that are farther away look more blue than those that are nearby. So atmospheric perspective, it's also called aerial perspective. So all that really is talking about is the distance between you and the object, right? The air between you and the object, the amount of air or atmosphere between you and the object affects its color. So you can see there, if you look at that piece of land there, that's kind of there on the right, it looks kind of brown. And if you look at the one behind it, it looks more blue. But it's actually probably the same color. Okay. And I don't know if you can tell with the water, but with the water also, the water that's more nearby toward the lower part of the image looks less blue than the water that's farther away. The water that's farther away should look a darker blue. All that is atmospheric perspective. So because of the amount of air or atmosphere between you and that object, it looks a certain kind of blue. And the farther away it looks, the more atmosphere there is between you and the object, the more blue it looks. Because our sky is blue. The air around us, well, it looks clear, right? But if we look through a whole bunch of it, it looks blue. That's why when you look up in the sky, it looks blue. Actually, there's another reason for that. I'm not going to get into it. That has to do with physics. But things that are farther away look more blue. If it looks more blue, okay, it's probably farther away. Okay, that's not always true, unless an object is really blue. But when you're looking at something farther away, it looks more blue, okay? That's what I'm saying, okay? And you can see that as you go outside, okay? You look at the mountains. Motion parallax, this one, you really have to be in motion to really see it. But motion parallax, and this is not an image of Baja, a picture of Baja. Motion parallax simply says that as we move, closer objects appear to pass by more quickly. And this accounts for a certain illusion, okay? Where the moon, or that might be the sun actually, where the sun, or even the moon, right, appears to follow you when you're driving, especially if there are clouds. If there are clouds and you're driving, what you'll see is that the clouds will pass by more quickly, but the moon or the sun stays in view longer. So it looks like it's chasing you. That's motion parallax. Why is that? Why does it look that way? Because the clouds are closer and they pass by sooner than the sun that is farther away. The sun stays in view longer, or the moon, and it looks like it's chasing you. You could also see it with things that are closer. When you're driving on the freeway and you see the little poles that, or the rail there with the little poles, the little studs that hold up the rail, right? You can see that as you're driving by, they pass by very quickly. I mean, you may not even be able to see them because they pass by so quickly. They appear to be transparent. But if you look at things in the distance, like houses, they stay in view longer. Okay, so they look like they follow you a little bit. Okay, but you can more easily see this with the sun or the moon. Okay, that's motion parallax. Things that are nearby pass by more quickly when you move than things that are farther away. And that creates kind of an illusion that something might be following you. You can see it more easily when things are really far away, like the sun or the moon. Okay, that's motion parallax. Another one is accommodation. We already mentioned accommodation, believe it or not. It's a monocular cue of depth perception as well. It tells us about distance. Accommodation is simply when your lens changes its shape to focus on an object. I mentioned this before. The lens changes its shape to focus on an object because you look at something and the lens can change its shape to try to focus the light at the back of the eye, at the retina, at the fovea, basically, so you can see clearly. Turns out that when you try to look at something that's far away, the lens has to stretch a little bit to focus clearly on that object. When you look at something that's nearby, the lens actually is squeezed on and gets a little bit more round or a little bit more compact to focus on that object clearly. That change in the shape of the lens is called accommodation and also tells your brain about distance. And it says there that a young soft lens can change its shape more easily than an old one, an old stiff lens. You're more likely to need glasses when you're older because your lens will get stiffer. It won't be as good at focusing. Okay. Some of you already wear glasses because it's already not that good. Okay, those are the monocular cues of depth perception. And now let's talk about something even more interesting. And I can show you a whole bunch of these, but I'm only going to show you a few. Let's talk about optical illusions. Like I said, we're talking about perception, but we're talking about visual perception, about how we make sense of what we see. Well, sometimes our senses can be fooled. Optical illusions are visual illusions. It's when we see something and it's not what it seems to be. So if we look here on the lines here on the left, believe it or not, that first black line there and the second one are exactly the same length. But one of them appears longer than the other. Why is that? It's because of the angles there that they have drawn that basically change the way you interpret the line. To give you more information, you can look at the image on the right. You can see that dark line there, those two dark lines. The one on the right is longer than the one on the left. And here's like you're looking at the inside of a house or something like that. But it's the context, right? It's those walls and those angles that make the line on the right look like it's farther away. And because it's the same length as the one on the left, you see it as being longer because you interpret that as, well, it's farther away, so it's longer. It looks longer. Your vision is being fooled here into thinking that it's longer, but it's exactly the same length. It's an optical illusion, a visual illusion. And by the way, that's what magicians do. They fool your senses, your vision. You think you're seeing something that is not really what you're looking at. It's something different. To take this even further, you can look at this, Ames room. Ames room is a room that was created that makes things appear to be different than they actually are. Believe it or not, those two girls there are exactly the same size. Why does one look so much bigger than the other? That's because your mind interprets that as being a regular room that's square, that has right angles and all that stuff. Notice the checkerboard pattern at the bottom, all that, right? The clock, there's a bunch of things going on here that are fooling your senses. If you were to look at that room in person and see the way it really is, you'll find that it's very distorted. The ceiling actually slopes down toward the girl on the right. It slopes down, it's lower there and it's taller on the left, okay? Those windows aren't really that shape. The clock isn't really circular. They're playing with a lot of these cues of distance to fool your senses. And in reality, right, those two girls are the same size. There's a link there. Actually, I'm not sure it's a link. You can copy and paste it and go look at it and it'll explain how that works. When I do this in class, then we look at it together. But remember, the videos don't play very well in Zoom. There's a problem with the sound. And I don't know why, but well, that's another illusion. You can look at it yourself. There's also the moon illusion. The moon is an illusion to some extent. When, you know, not an illusion, but here's the thing. It creates an illusion. When you look at the moon high in the sky, it looks small. But when you look at it close to the horizon, when it's close to the horizon, it looks huge. It looks a lot bigger. But the moon is exactly the same size. And you can even take a quarter and compare the moon high in the sky and the moon by the horizon. You'll see that's exactly the same size. Why does it look so much bigger when it's by the horizon? It's not completely understood, but one reason is that when you look at the moon by the horizon, you can compare it with the mountains and the trees, and you know those are big, and the moon is even bigger, so the moon looks huge in comparison. When you see the moon high in the sky, well, you compare the moon to the huge sky, and the moon looks small in comparison. There's other things that affect the illusion, but it's an illusion. And now I'm talking about the moon. I can tell you about another illusion that I learned about recently. You know, when you're looking at the sunset, like when it's just about to set, like 5 minutes before it sets, believe it or not, the sun isn't there anymore. It's not even there. You are looking at an illusion. There's several reasons why you're looking at an illusion. First of all, it takes the light, okay, about 8 minutes and 20 seconds to reach us. So the sun has already set by the time the light hits your eyes, okay? But even if the light from the sun were to appear at your eyes instantly, it would still be an illusion. The sun set 5 minutes ago. You can still see it, but it's set 5 minutes ago. Why is that? It's because of refraction, because the light is bending and you can see the sun even though it has already set. The sun should not be visible anymore. That's also an illusion, but it's one you're not aware of. I learned that recently by watching a YouTube video with Neil deGrasse Tyson, that famous, what is he, an astrophysicist, I think he is. He talks about space and all kinds of things. He has a lot of interesting videos. So that's one illusion I learned about. He talks about a lot of things and try to explain them from a science point of view. There's all kinds of illusions, okay? There's also the hollow face illusion. And, you know, if we were doing this face-to-face, I would play that video and you would see how this works. It's very interesting, okay? The hollow face illusion, basically, what happens is when you're looking at, this is just, let's say, a mask of Einstein, and it sticks out in a certain way. It sticks out on one end, and you know, like when you look at a mask, and you look a hollow mask, you look at the other side, and the other side, it's basically concave. It's inward, right? It's hollow on the other side. Well, it turns out that when you look at a mask like this and you rotate it, it always looks like it's sticking out. Whether you're looking at the side that sticks out or you're looking at the side that is hollow, that basically sticks in or that goes in, it'll always look like it's sticking out. Check out the video and you'll see. There's a lot of illusions out there, a lot of interesting illusions. These are just a few, but it's just to make the point that your senses can be fooled, okay? And there's many reasons why they are fooled, because of prior information, because of top-down processing, because of the context, the way we compare things, or the way we understand things. There's a lot of illusions. These are just some examples. So I encourage you to check them out on your own, and you'll see how interesting they are. And when you go to YouTube, you'll find other illusions as well. there's also a funny one that comes up after this one, plays right after. And by the way, if the link doesn't work, because the problem is that in YouTube, sometimes the things change and the address doesn't stay the same, and then you have a certain link, and then you click on it, and it takes you to a different video, which is not the one that was meant. I'm pretty sure I updated it, but if it doesn't work, just look for hollow face illusion, or look for some other thing, some other illusion, visual illusions, and you'll see lots of them. And there's some very interesting ones, and there's some that are actually funny. Okay, that is where we will stop. I will stop recording.